Okay, this is for Math 1, Lesson 1.4.1. And what we're talking about in this lesson is inequalities. And the book refers to them, which I like, as like constraints and restrictions. So here's the important overarching objective is that inequalities, instead of solving an equation and getting a single answer, like x equals 2, we now have a range or a set of answers. And what defines that set of answers are different restrictions or constraints. And a lot of times we refer to those as like the linear portions and the lines within our graph here. So in these examples, we're going to talk about, what are these constraints and how do we define them? So let's first take a look at this first example. It says determine whether the ordered pair, the coordinate -2, 9, is a solution of the inequality here. So here we have an equation. So we want to know if this is a point. So even though we're plugging in or evaluating two different pieces, we're still testing a single solution. So this is a single solution. Okay, so this is this, um, is it a solution? Yes or no? So we don't know yet. I'm going to test it. Okay. Um, so what we want to do is plug it in, evaluate it. So the original equation is y is less than or equal to 5x plus 6. Now, we're going to substitute the x and y with these two values. So I'm going to plug in -2 for x and put 9 in for y, and then simplify from there. So -10 plus 6, -10 plus 6 is -4. Now notice, is 9 less than -4? And the answer is no. So this is a false statement, which means that -2, 9 is not a solution. Okay, so let's go ahead and take a look at the graph what this looks like. So based on what we know about graphing, I'm going to find my starting point and my rate of change, which is up 5 over 1. And I'm just going to draw a line here, 5, 1, 5, 1, and 5, 1. So I just kind of got some guide points that goes forever. Okay. Now notice if we plotted this point, the answer is not just that line. The answer is actually any point that is in the yellow region, that line, and anything over here. And it forever goes that way and forever goes that way. Okay. Now notice if we plot this point, -9 or -2, 9, that point right there, that is not in the right region. Now let's go just pick a random point and see if it is in the region. So I'm going to first pick a point on the line. So I'm going to pick the point -1, 1. So now if we plug this in, okay, so let me kind of erase what we have here. Just get this example out of the way. I'm going to plug in a new example. I have, I'm going to test the point, what is it, -1, comma 1. So -1 goes in for x, 1 goes in for y, and we have 5, -5 plus 6 is 1. So is 1 less than or equal to 1? And the answer is yes. Now notice it works out perfectly the same. So this is where the equal part comes into it. Now if that wasn't there, this wouldn't be the case. So since it's on the line, it is included. Now let's pick another point. I'm going to, again, eliminate this, and we're going to test another point. So notice I'm just using the same piece here. And we're going to test the point. Let's pick a point over here, right there, just anywhere in this yellow region. So we have this ordered pair is, what is that, 4, comma 2. So I'm going to test the point 4, comma 2. So again, plug 2 in for x, plug 2 in for y, I'm sorry, plug 4 in for x, going backwards. So is 2 less than or equal to 20 plus 6, which is 26? And the answer is yes, 2 is less than 26. So this is, yes, a solution. Okay. So notice any point in this region over here works. So anything over here is an answer. So it's not a single point, it's a set of points. The line's included in this case. Now, if that line wasn't there, if the inequality, that'd be a dashed line and wouldn't be included. Anything over in this region is not included, not a solution. So again, we're talking about constraints, which is defined by the line there, but the actual answer is the yellow area. So let's kind of take a look here at, an application of sorts. Taxi company charges $2.50 plus $1.10 for each mile driven. Write an equation that represents the situation. Okay, so we write it as a equation. Um, it really should be an expression right now, so we'll change it to an expression. We started with $2.50, which when you get into the cab, plus $1.10 for each mile. And again, M is the number of miles driven. Okay. Now, the second part says use this equation to determine how far you can travel if you have $10. Now, here's what comes later. You have $10. Now, can you go over or under $10? Now, if you spend more than $10, you're not going to have enough money. But let's say you only spend $9. Is that okay? For sure. So the equation has to be less than or equal to $10. So how does the equation portion, or I should really say the expression on this side, how does the expression on this side relate to, you know, um, the constraint of $10? Okay. So when we do this, let's go ahead and solve for m. So we're going to have 1.1m. I'm going to subtract the $2.50 from both sides. And notice we get $7.50. Okay. To get m by itself, I'm going to divide by the inequality. Okay. So I'm going to use my calculator here. And we get anywhere up to 6.81 repeating miles. Okay, so obviously you could drive 5 miles, you could drive 4 miles, 4.5 miles, anything up to 6.8 miles. Okay, so obviously if you're going 7 miles, you're not going to have enough money. So there's your limitations of where you're at. Okay, now thing two, just kind of off to the side. A lot of people ask, when do you ever switch the sign of inequality? When you introduce a negative. So here's a little example. Let's say 2 is less than 3. That, this kind of little bonus corner over here. 2 is less than 3. Now, the moment that you introduce a negative into the equation, -2 and -3, is -2 less than -3? No, it's not. -2 is bigger than -3. So notice if you switch the signs of the numbers, you have to switch the sign of the inequality. Okay, so this is an example of when you switch. Okay, so that comes into play quite a bit too. All right, let's look at the last example for this lesson. School supply company produces wooden rulers and plastic rulers. The rulers must first be made and then be painted. Okay, so here's where we talk about restrictions. So you have the function that we're talking about is that you have to produce rulers and wooden rulers and plastic rulers, but you have different restrictions. Amount of time you have to make them and paint them. So we have to be able to write a system, a single function that has all these constraints together. So let's talk about what we have here. It takes 20 minutes to make a wooden ruler, 15 minutes to make a plastic ruler. There's a maximum of 480 minutes per day set aside for making rulers. Okay, so let's first identify our variables. So I'm going to say W for the number of wooden rulers. Sorry, my pen's not working there. And I'm going to use P for the number of plastic rulers. Now again, I always like to use variables that identify what I'm talking about. And then sometimes you got to translate them to an X, Y coordinate if you're using it, but just change your labels. Number of plastic rulers. So to do this, if it takes 20 minutes per wooden ruler plus 15 minutes per plastic rulers, the time it takes, that has to be less than or equal to 48. You can't go over 480 minutes. Now you can go short of, let's say it only takes you 470. That's fine. You got 10 minutes to spare. So that's the first restriction, first equation that defines a constraint. It takes 5 minutes on the second part. So I'll do this in, also was in red. I'll do this one in black. It takes 5 minutes to paint a ruler, 2 minutes to paint a plastic one. There's a maximum of 180 minutes for painting. So again, 5 minutes per wooden ruler, 2 minutes for a plastic ruler, and they set aside 180 minutes. So again, it has to be less than or equal to. Okay. Now, here's the other thing. let's talk, we talk about domain and range and things like that. Is it possible to make negative rulers? Well, I guess if you start breaking them or something, who knows? But the number of wooden rulers, that itself has to be bigger than or equal to 0 because you're making rulers in positive numbers, okay? Same with plastic rulers. It has to be bigger than or equal to 0. So the reason why you have to define this is because when you go through the math, if you use your calculator or a graph, whatever, they don't know the context of the problem. So you have to define the context of the problem, saying, no, if we make rulers, we use positive numbers. We don't make negative rulers. Now, these all constraints have to work together. So we call this a system. So we put it in a bracket like this. And this right here defines the fact that it's a system. Okay. And that's what we're shooting for here. Okay. So these four constraints are working together to produce a scenario, the function, how many wooden and plastic rulers can we make given these constraints.